A standard Liebherr 280 ECH requires 100 meters of height for a modern skyscraper, yet the initial base section only reaches 40 meters. The solution is self-climbing, relying on the telescoping principle, where the crane uses its own power to lift its superstructure. The key component is the climbing frame, or jumping frame, which temporarily supports the entire weight of the slewing unit, jib, and counterweights. This frame is essentially a hydraulic jack system integrated around the mast. The crane must be temporarily unloaded or operate at severely reduced capacity during the climb. The maximum height achievable is limited only by the structural tie-ins to the building core and the mast section's compression strength. The climbing frame is a robust steel structure encompassing the mast, typically spanning 2 or 3 tower sections. It contains powerful hydraulic cylinders, often operating at pressures exceeding 200 bar, providing the necessary lifting force. These cylinders are mounted on a fixed collar that grips the lower, already secured mast sections. When activated, the cylinders push the upper collar, which supports the slewing unit, upwards by the height of one new mast section, usually 3 to 6 meters. This movement creates a gap directly beneath the slewing unit, precisely sized for the insertion of the next tower segment. The frame ensures the crane remains perfectly plumb and centered throughout the lift sequence. Tower sections are standardized lattice structures, usually square or triangular, designed for high compressive and bending loads. They are fabricated from high-strength steel, often S355 or equivalent, optimized for weight and rigidity. The typical section length is 3 to 6 meters. Connections between sections are critical, relying on large high-tensile strength bolts, often M36 or M42, torqued to specific values, sometimes exceeding 1,000 Newton-meters. These connections must distribute the massive vertical load and resist the overturning moment generated by the jib and load. The precise alignment during insertion is maintained by guide rollers within the climbing frame, preventing eccentric loading during the critical joining phase. The climbing sequence begins with the crane lifting the new tower section from the ground or a staging area using its own hoist mechanism. The section is suspended directly beneath the slewing unit. The hydraulic cylinders in the climbing frame extend, lifting the entire upper structure. Once the gap is created, the suspended section is maneuvered into the space. Guide pins ensure initial alignment. Workers then secure the new section to the existing mast below and the slewing unit above using the high-tensile bolts. After torquing is complete, the hydraulic pressure is released, transferring the load back onto the newly extended mast. The entire process, including bolting and inspection, typically takes 4 to 8 hours per section.
As the crane height increases, the overturning moment from wind and operational loads becomes the primary structural concern. Tower cranes must be anchored to the building structure using tie-ins, typically heavy steel collars connected to the building's concrete core or structural frame. These tie-ins are spaced vertically according to engineering specifications, usually every 30 to 40 meters, depending on the crane model and wind zone. The tie-in design must account for thermal expansion and differential settlement between the crane mast and the building. Failure to install tie-ins correctly is the leading cause of catastrophic crane collapse, making rigorous inspection mandatory before any further climbing operation. During the climbing operation, the crane's operational envelope is severely restricted. The maximum permissible load is often reduced by 50 to 75%, and slewing speeds are minimized to prevent dynamic loading on the temporary support structure. Safety protocols mandate that no personnel are permitted beneath the climbing frame during the hydraulic lift phase. The climbing operation is highly sensitive to wind speed. Most manufacturers prohibit climbing when wind speeds exceed 15 meters per second, or approximately 30 knots. This constraint often forces climbing operations into early morning hours or specific weather windows, impacting construction schedules and increasing labor costs for specialized rigging crews. Tower cranes are rarely purchased outright by construction firms. They are typically leased from specialized equipment rental companies. The rental rate is calculated based on the crane model, maximum height required, and duration of the lease, often structured monthly. Operational costs include specialized rigging labor, required for assembly, climbing, and dismantling, which commands premium wages due to the inherent risk and technical skill. Energy consumption for the hoist and slewing motors is significant, often requiring dedicated high-voltage power feeds, typically 480 volts 3-phase. The cost of the climbing operation itself, including hydraulic fluid, labor, and downtime, can exceed $15,000 per jump, depending on location and complexity. Regulatory bodies, such as OSHA in the United States or similar national agencies, mandate strict certification requirements for crane operators and rigging personnel. Every tower crane must undergo a thorough inspection by a certified engineer before initial erection and after every major structural alteration, including each climbing operation. The crane's logbook must document all maintenance, repairs, and structural changes. Load charts and wind speed limitations are legally binding operational parameters. Failure to adhere to these regulations results in immediate site shutdown, substantial financial penalties, and potential criminal liability for site managers in the event of an accident. Once the building is complete, the crane must descend, reversing the climbing process by removing sections. The final challenge is removing the crane itself from the top of the structure. This is achieved using the small crane paradox. A smaller, lighter crane, often a mobile hydraulic crane or a specialized derrick, is lifted to the roof by the main tower crane before the final descent begins. This smaller crane then dismantles the main crane piece by piece, lowering the components to the ground. Finally, the small crane is disassembled into manageable pieces and lowered by the building service elevator or a temporary host system.